Okay, this is math reasoning for April 9th. Let's get started. Okay, so today we're going to start chapter 2, chapter 2 on language and proofs. In some sense, this is the main core of this class. But so what you need to learn in this quarter, most of it is contained here, but you have to have some realistic expectations. You're not going to learn everything there is to know about writing proofs in one chapter in 1 week. Um, this is something that you get better and better at as you practice. So although this is the core, we're gonna be hitting and practicing these types of ideas throughout the quarter. This chapter, I think, naturally breaks up into 4 different videos. This video, we're going to introduce a couple different proofs and just kind of talk about like meta things. Like we'll talk through the proof about what it's proving, but at the same time, focus more on the structure of the proof itself rather than what it's proving. And on the next video, we'll talk about some basic logical statements and connectives that you can build more complex logical statements out of. But let's start with the sample proofs. So here's there's 2 different proofs that we're gonna walk through. Both of these proofs will take about a page to prove. So try to follow along and focus on the structural proof, how you would kind of go about it, I guess. All right. So the first theorem is about linear equations. So let's read the statement. Okay. So let's say we have ax plus by equals to r and cx plus dy equals to s. So these are 2 linear equations in 2 variables, x and y. Notice before we go any further, notice when you write out this statement of the theorem, you might expect the audience to know what linear equations are, but even then you still write out the 2 equations, ax plus by equals to r and cx plus dy equals to s. So this is doing 2 things. One, it's reminding the audience that that's what linear equations are in 2 variables, x and y. And also at the same time, it's introducing all the variables and coefficients that you're going to be using. So you're setting up the notation at the same time. Oop. That's strange. Okay. So if AD minus BC is not equal to 0, then there is a unique common solution. So unique as in there's only one answer, and common solution as in you have an x and y pair that satisfies both equation 1 and 2 at the same time. Graphically speaking, it's looking at the intersection of 2 different lines. That's what it means by common solution. If AD minus BC is equal to 0, then there's 2 choices. There's either no common solution or there are infinitely many solutions, depending on the value of R and S. So you could imagine a situation where AD minus BC is equal to 0 corresponds to a picture where you have 2 parallel lines. So if they're parallel, then they don't intersect, so there's no common solution. Or if they happen to be 2 identical lines, then pretty much everything along that line is a solution. So then there would be infinitely many. And this theorem is kind of stating that there's really these three possibilities. Either there's exactly one solution, no solution, or if there's more than one, then it has to be infinitely many. This might be something that you're very familiar with if you take a matrix algebra class, and maybe you have some intuition about what AD minus BC being equal to 0 or not equal to 0. But let's jump into the proof and see how this is proved here. Okay. So the first stage is to kind of get rid of a stupid case. So if all of the coefficients A, B, C, and D are equal to 0, in which case you kind of have a stupid equation, right? If A, B, C, and D are all zeros, that means the equation becomes R equals to 0 and S equals to 0 with no variables X and Y. So they could really be anything. So then there is no solution unless R and S happen to be 0, then both equations are satisfied no matter what an X and Y is. So in which case, all pairs X and Y are solutions. That's kind of the stupid case that you kind of want to get rid of. But if that's not the case, if not everything is equal to 0, then that means there's at least one coefficient that is non-zero. So it could be A, B, C, or D. And assume without loss of generality that D is not equal to 0. This is a very handy phrase to use. So we have a situation where the opposite of everything equal to 0 is at least one of them is non-zero. It seems like to consider all possibilities, you have to look at, well, in the case where A is not equal to 0, or if A is 0, but maybe B is not equal to 0, and so on. But you can kind of see that all of these are kind of result in a very similar type of argument. So if there's no basic difference in the type of argument you're going to make, the phrase you usually use in a proof is called is assume without loss of generality. So, you know, it could be A, it could be B, it could be C, or it could be D that's not equal to 0, but they're all pretty much the same. So let's just assume it was in the case where D is not equal to 0. And the rest should follow a very similar pattern. If there's genuinely different type of argument used, you shouldn't be using this phrase and only prove one case. But if it's very reasonable, in this case, I mean, being D not equal to 0 and B not being equal to 0 is the same thing if you flip the equation 1 and 2, really. Like, it's just a label. And even in case where A or C is not equal to 0, if you relabel the two variables X and Y, they're pretty much acting in the same fashion here. Then it's pretty much the same argument still. So I think this is a reasonable case to do. Okay, so, okay, what if one of the coefficient D was not equal to 0? Then you can divide by that coefficient. So you can actually solve for Y in the second equation. And that's what we have here. And once you can solve for Y, you can plug it into the first equation, 1. And this is what you get after collecting like terms. So after you plug it in for Y, you collect the coefficient of X together, and this is what you get. And this is the constant term. Then you have this equation. you could get this a little bit simpler and get rid of the denominator d if you multiply the both sides of the equation by d. And here's what you get. And this is now looking more promising because we get this AD minus BC. And now this being equal to 0 and not equal to 0, you could see why this would make a difference here. So we're getting closer. When AD minus BC is not equal to 0, so as long as the coefficient of x is not 0, you could divide by it and you can solve for x. And if you solve for x, this is what you get. And if you plug this x into equation for y, that's this equation where we substituted. Yeah, that's the equation 2, right? If you plug it in for x there, here's what you get for y. So combine those two together. This is the unique solution. Right? There's only one solution here. We've solved for both x and y. This is the case where AD minus BC was not equal to 0. Then you could solve for the solution. The second part of the solution was that if they're equal to 0, then you either have 0 or infinitely many solutions. So let's work on there. If AD minus BC is equal to 0, then let's see, this equation right here that we had earlier, this equation, if this coefficient was equal to 0, it's just reduced to BS is equal to RD. So that might be true or that might not be true. So if BS is not equal to RD, then there's no way to make that equation true. So there's no solution. If BS is equal to RD, then this equation, BS is equal to RD, it's always true for no matter what x you plug in, because x doesn't even appear there, right? So in that case, you could choose x to be anything you want, any real number. And then after choosing x, you can plug it into equation for y here. Equation for y is here. So once you choose your x, plug it in for y. And then you get a solution for each x you can choose, right? So x could be any real number. And then as long as you choose y so that it's compatible with your choice of x, then you get your infinitely many solutions. So that's the proof. Okay. So I want to draw attention to a couple of the things in that proof. This is what's called existence and uniqueness type of proof. So in mathematics, sometimes you ask a question and it's not obvious if there's a solution or not. And if there is a solution, is there multiple solutions or is there only one solution? These are type of questions that you have to ask before saying like, what's the solution, right? So this is like here's how I would think about it. If you ask, not to get too philosophical, but if you ask a mathematician, hey, what's the meaning of life? Mathematician would say, actually, before you ask that question, you should ask, is there a meaning to life? And if there is one, is there only one meaning to life or is there many? So existence and uniqueness is type of questions that maybe if you've taken matrix algebra or differential equations class before, then you know that these type of theorems exist. But as you take more upper division math courses or computer science courses, these will become more important. Like as you consider more complex problems, it's not at all obvious if the solution is there, or if there is a solution, is there only one solution, or is there lots of different solutions that's possible? In fact, my PhD dissertation, 1/3 of my dissertation was focused on, hey, did I ask a question that has an answer, and is there only one answer? So 1/3 of it was trying to convince the reader that I asked a good question, that there is a solution. Okay, another thing to keep in mind when you read this proof is that proof is not written linearly. The person who wrote this theorem, whoever it is, did not start. Sorry, let me go to the statement of the proof. Sorry, theorem. They did not start writing the theorem saying, okay, all right, so I have two linear equations and AD minus BC, this is gonna be the important difference between the different situations. That seems like a out of nowhere. And if you just read this theorem, you might ask yourself, how would I know that's the theorem to write down? Like, how do you know that you should even focus on this quantity AD minus BC? The answer here is that they didn't. What they did was they looked at two linear equations and they wanted to write down a solution for it, and they started writing it down. And then they realized that the solution that they came up with, assuming that they're allowed to do anything they want, they get this solution while they're working on the solution, and then realize, hey, this would make sense as long as like AD minus BC is not equal to 0. As long as we're not dividing by 0, this expression makes sense, and I can plug it in, and that satisfies the two equations. As of all writing, the author did not start from the very first line of the first chapter and started writing without any mistakes, and at the end say, this is my final version that I'm going to submit to the publisher. That's not what happened. They solved for it, and then they realized AD minus BC is a special case where if that is equal to 0, then the whole analysis changes. So they went back to their theorem statement and then said, okay, you could solve this as long as this is not 0. And if it's 0, they carefully considered what would happen in that case. So don't think when you look at a theorem and wonder, like, I wouldn't have ever come up with that on my own, or like, how do you know, how did they know that they started with this? It's most likely that they did not start with that. And they kept on revising their proof until everything fell into place. And then that's the final version of the proof that gets printed on a textbook and so on. So you should get used to that. There are drafts to proofs, and in the drafts, you can change the statement of the theorem that you want to prove as well. That's part of the game. I think it's important to realize that you go back and forth when you're writing a proof. Okay. And I've already kind of stated this, but avoiding division by 0 leads to exceptional cases in this theorem. So you should always worry about edge cases where things might break down. And if you have to change the analysis to treat those cases separately, then you should do that and add those as exceptions in the theorem statement, or change the theorem statement so that the edge cases are irrelevant. Log. So, I mean, this is the shorthand for assume without loss of generality. So that's the place where you assumed at least one of the coefficient was non-zero. So let's just assume it's D. So the author of this proof was able to use that to their advantage. And without repeating very similar type of argument 4 times, instead they just said, well, assume without loss of generality, just consider this one case. Everything else is similar. So there are a lot of opportunities where you could say something like that. So try to keep that in mind. That's a useful phrase. And when you write down proofs, you're going to be asking this question to yourself many, many times. How much details are required in this proof? And probably the non-satisfying answer that you're going to hear is that, well, it depends. It really depends on the audience. So as of any type of writing, I would write the proof of this theorem differently if I was writing it for other mathematicians, or if I'm writing it for algebra students, like intermediate algebra students in maybe middle or high school, or if I'm writing it towards like beginning math majors or computer science majors like yourselves. So really the details depend on what you think the audience knows and able to handle themselves. For example, in this proof, I think some of the algebra was skipped, right? When you substituted y into the first equation, I just jumped to collecting like terms with x without the intermediate step. Again here, after x was obtained, yeah, plug it in, y yields this solution. And that takes a couple steps of work, but the audience was trusted to work out those intermediate steps. If I was writing this for intermediate algebra students, I would not do that. I would go into more detail. If I was writing it for other mathematicians, this proof would not be a page long. It would be a few lines long, maybe 3 or 4 lines long. So how much details are required? That's something that depends for the audience. For this class though, what I want you to do is lean heavily on, if you are asking that question, then probably, yes, you do need to include more details. So the reason why I say that is for 2 reasons. Number one, I will never penalize you for having too much detail when I'm grading. But if you do not include not enough detail, then I will penalize you for homework. So it's safer in that sense. That if you're not sure, then probably include more detail. And another reason why I kind of want you to lean heavily towards including more details than necessary is that I think you'll find that even if there are statements that sounds absolutely obvious to you, that of course this is true, like this has to be the case. A lot of times when you try to include the details, you realize that you actually didn't realize there was enough. You realize you didn't know enough definitions to go into detail, and you might be forced to kind of go back on the textbook to look up definitions, or you realize that there's actually more details there than you expected when you first assumed that maybe this isn't a detail that I don't have to go into. I think you'll surprise yourself that there's a lot of details that that you'll be glad that you retaught yourself that stuff because when you try to write it down, maybe you couldn't right away. I think that's common. So I want you to get into the habit of that. And then, like at some point, if you become a mathematician in master's or PhD level, at some point you have to start dropping details. But undergraduate mathematics and beginning graduate school mathematics, I think you should be going into more details than not. You really have to cut back on the details when there's a restriction for publishing. So if you're writing a book or if you're publishing a paper, then they want to cut back on your paper so that more papers could be published. So that's the case where you start to worrying about cutting details. But with homework, there's no penalty for having too long of a homework solution. So please err in the side of including too much details rather than not. Okay, let's move on to the next theorem. I think this next theorem is actually quite beautiful. Okay, so let's say you have 3 integers, so A, B, C are all odd integers. And you have this quadratic equation, ax squared plus bx plus c. If A, B, C are all odd, then it has no solution in the set of rational numbers. So we know we can find the solution probably by using quadratic formula, but the quadratic formula will not yield a nice rational number. It'll include some square root of something that's going to be irrational. So let's jump into the proof of how you might prove something like this. Okay, so in the proof, you first assume that there is a rational solution. So you have a solution x where you could write it as a ratio of 2 integers p and q. So x is equal to p divided by q. And when you write this down, p and q, this is a ratio that you're introducing. You could choose it in such a way that they have no common factors. So you could reduce, if there's a common factor, you can kind of cancel them out and put it in a reduced form. So there are no common factors. In particular, they can't both be even, right? If p and q are both even numbers, then you can factor out the 2 and divide by it. So either they're both odd or at most one of them is even. They can't both be even. Okay, so we have this equation ax squared plus bx plus c equals to 0. Let's plug in the p divided by q in for x. Okay. If you plug it in and kind of multiply both sides by q squared, this is the equation we get. ap squared plus bpq plus cq squared. And that's still equal to 0 because 0 times q squared is still 0. Okay, so we have this quadratic terms with three terms. So what we want to do is we're going to get a contradiction by showing that this whatever this is, it cannot be equal to 0. We're going to do this, so we want to show that it's not equal to 0, and we're going to do this by proving that it's whatever this expression is, it has to be odd, right? If it's odd, then it can't be equal to 0 because 0 is an even number. Okay. So let's look at all the cases. So what we know is that A, B, and C are all odd numbers, and P and Q, at least one of them is not even, right? They can both be even. So let's say P and Q are both odd. So if both are odd, then all of these three terms are product of odd numbers. So odd number times odd number is always odd. So those three terms are all odd in the end. And if you add three odd terms, you're gonna get an odd number. So product of odd numbers is odd, and sum of three odd numbers is odd. So you have an odd number in the end. Okay, so what if at least one of them is even? So if P is even and Q is odd, or vice versa, maybe P is odd but Q is even, in that case, out of the three terms, 2 out of the 3 will be even and one of them will be odd. So let's say if P was odd, so that one will be odd. But if Q is even, once you multiply in an even number, it's gonna be, it remains an even number. So odd plus even is gonna be an odd number, and it's gonna be odd in the end. So in each case, the assumption of rational solution leads to a contradiction, right? So it cannot be odd and equal to 0 at the same time. So that's the contradiction here. So what if there's a contradiction? Why is that bad? Well, the only thing that you really assumed without any proof is that you assume that there's a rational solution. So if you assumed something and you ended up with something that's impossible in the end, so an expression is equal to 0, but it's also odd at the same time, that's impossible. So whatever you assumed must have been wrong, right? So that means that there must have been no solution that are rational numbers. So that's the idea of the proof. So this is kind of interesting because this is an example of a non-existence proof. So you're kind of saying that no matter what you try, this cannot happen. So you need a clever kind of generalization to prove something like this. So I thought that was it's an interesting type of proof to look at. And I guess the first proof did that as well, but again, in this case, the proof deals with cases. So in the cases where P's and Q are both odd, or one of them is equal to even and the other one is odd. And each of those cases, some kind of contradiction happened. Okay, so this is a type of proof technique that we'll consider. One more thing I want to say about this theorem. You might worry that, like, how would you think to do that, right? How would you think to look at x is equal to p over q, and consider the cases where they're both odd and one of them is even, and so on. So you might be discouraged that like maybe I'll never come up with these type of proofs because I wouldn't, like, how would you even start to think about that? um, I wouldn't worry too much about having the originality of like what to try in this class. The reason why I say that is because this is like a number theory type of theorem and a proof, and these aren't these don't appear out of nowhere. It's not in isolation. So if you're starting to study number theory, then you will be exposed to lots of arguments that look like this. So, so this would be a reasonable thing to try once you're exposed to those sets of theorems and proof when you're learning the subject. Um, you don't have to be a super original genius to do this type of mathematics. That's a that's a misconception, I think. These are type of standard things that you do try once you get the hang of the types of arguments that's used in the subject. Okay, so I think this is where I want to end this video, and I'll see you on the logic video next.